Building the Wolverine Amplifier, Initial Distortion Measurements. In this video, where we left off, basic power supply setup used for testing, what is distortion, why should you care, and does class A, AB or B matter, how is distortion measured, my measurement setup, and a baseline THD plus N measurement of the Wolverine amplifier with the current bill of materials at 20th of the 8th, 2022. Where we left off. In the last video, we finished around this point where I was showing some sine wave measurements. Up until now, I've been using the power supply from another amplifier and two programmable laboratory power supplies. In this video, I'm going to use a basic linear power supply. A few people have asked me about power supplies, so let's start off by having a look at the power supply setup I'm using. You can see from the simplified diagram on the left, it is a regular linear power supply using a transformer and two full wave bridge rectifiers, and two electrolytic capacitors. I'm using an audio ground lift circuit which connects the power supply 0 volt connection to the chassis of the amplifier through the ground lift circuit above. This is an important step from a noise point of view, and you can see the circuit on the right hand side above. Please note it's very important that the chassis and heat sinks are still connected to mains earth for safety reasons. Here's a picture of the power supply I'm using currently for testing. I use a Schaffner FN9290-10-06 power inlet module, which has a built-in two-stage filter, a double pole switch, and fuses on both active and neutral. This feeds into a toroidal transformer feeding two 35 amp bridge rectifiers, two 33,000 microfarad electrolytic capacitors, with 100 nanofarad bypass capacitors in parallel. I use blue LEDs in series with 4.7K 5 watt resistors for indicators to show when the power supply capacitors are discharged enough to be safe to work on. This setup is what I'll be using for the distortion measurements later in this video. I plan to use a larger toroidal transformer, or perhaps two, for the final build. I use two inexpensive multimeters to monitor the rail voltages, and you can see the small green circuit board which has the ground lift circuit on it. Please note the mains earth is still connected to the heatsink of the amplifier. So, what is distortion? By definition from the online Cambridge Dictionary, to distort is to change the shape of something so that it looks strange or unnatural. If you have a further look, there's an example related to sound. To make sound produced on electrical equipment sound strange and unpleasant because of changes in the shape of the sound wave. The examples given are a powerful amplifier capable of producing sound at high volume without distorting it, or the sound system distorted the vocals. After reading the definition of the word distort, what is distortion in the context we're going to look at today? In simplistic terms, distortion is any unwanted addition or change of the original signal apart from amplification. Distortion in the context we're talking about is usually called THD, or total harmonic distortion, and it is the percentage of the output signal which is due to harmonics generated by the amplifier for a given input frequency tone and output power, where V1 is the fundamental voltage in RMS, and V2 to the N and so on are the harmonics. The equation looks like this. We'll also be showing THD plus N in some of the measurements, which is similar to THD above, but with noise added to the numerator of the equation. THD plus N is typically reported instead of THD, since noise is part of the measurement. Why should you care about achieving low distortion? Well, distortion is an indicator of how much your amplifier alters the original signal, in example, the music, as it's amplified. So if you achieve low distortion, it greatly reduces the chance of anything happening to the original signal other than amplification. Simply put, everything has to be working well to achieve low distortion and noise. There are some people who like colouring the sound, resulting in higher distortion numbers during the amplification step. And there are many arguments in the audio world about subjective opinions versus objective measurements. Both points of view have valid arguments and ideas behind them, but for today's video, we're going to have a look at the objective measurement of the THD for the Wolverine amplifier. Recently, a few people asked me, is more bias better? Is Class A better than Class AB? This question is not that simple to answer. One of the reasons Class A is used is to minimize crossover distortion and other nonlinearities. Unfortunately, not all designs are optimal even if they are running in Class A. More is not automatically better. Better is better. Bias should be set to a value which provides the optimum performance for a given design topology to reduce crossover distortion. As an example, the Wolverine amplifier is a Class AB amplifier that has been optimized for high performance and low distortion. Since it uses multiple output pairs biased appropriately, there is a reasonable Class A region. With Class AB and Class B amplifiers, if they're biased correctly, you can have very low distortion at both low powers and also higher powers. There is no free lunch with this, however, since there will still be heat generated. Perhaps part of the reason for the question above is because sometimes people underbias Class AB amplifiers to save money on power and heat sinking, which impairs the performance. This topic can get quite complex, and it's really outside the scope of this video. For more information, I would encourage you to check out the excellent amplifier books available from Bob Cordell, Douglas Self, and G. Randy Sloan. How is distortion measured? What devices are available to measure distortion? In general, THD is measured with an audio analyzer. Historically, audio analyzers have been quite expensive, but nowadays you can make do with an external PC sound card or an audio interface. And free software packages are available such as ARTA and REW. There are also some very nice analyzers made by Quantasylum such as the QA401, 2 and 3 and so on. Pictured above is some older analog equipment. Let's have a quick look at some other audio analyzers. Here is a HP 8903A audio analyzer. Here is an Amber 5501, the Panasonic VP7722A, the very nice Rohde & Schwarz UPV. Nowadays, you can also take measurements using an external sound card or a Pro Audio interface. This older Sound Blaster X-Fi is what I first used with ARTA software for some basic audio measurements. I have also tried a Steinberg and some others some time ago. I've also used a Focusrite Scarlett 2i2 version 3, which is a commonly used audio interface suitable for basic THD measurements. I'm recording this audio on a Scarlett 2i2 version 3 as we speak, mainly because it has a built-in 48 volt phantom power for the microphone I'm using. This is the Quantasylum QA401 that I mentioned earlier. It has software which allows you to run some automated measurements. There are a few new models since this one was released. Keithley make a THD multimeter. Keysight make a very nice audio analyzer called the U8903B. Since my background is laboratory tested measurement, more specifically electrical calibration, I sometimes get sidetracked by measurement equipment. Anyhow, I hope the previous slides give you some idea of a few of the instruments out there. This leads us to what instrument is usually considered the industry standard for audio distortion measurement. The Audio Precision APX555B. Its audio signal generator performance is the lowest curve on this graph. Have a look at the specifications here and you can see the generator will output a sine wave with typically less than minus 120 dB total harmonic distortion plus noise at 2 volts output. The analyzer will also measure at minus 120 dB total harmonic distortion plus noise at a kilohertz at 2 volt. Note that both of these are with a 22 kilohertz bandwidth. All this is great, but the price tag is not, since depending on options, one of these costs around $30,000 US. So now that we've seen the industry standard and we've had a look at what options are available, let's have a look at what a distortion measurement looks like. What does distortion look like? Here's a screenshot of a typical distortion measurement using an audio interface and software package called REW. So that you get a feel for what we're looking at, here are some tips. The large spike approximately in the middle is the fundamental. It's the actual signal that we're looking at. It is sometimes called the carrier, and on the left you see the y-axis is labeled dBc, which means decibels relative to the carrier. I will use dBc throughout since the fundamental level is automatically set at 0 dB regardless of the input level to the measurement device. Now that you know where the signal is, where is the distortion? So if you look at this FFT capture, which is averaged heavily so that you can clearly see the distortion circled in red, the REW software shows the distortion harmonics numbered clearly. For example, the fundamental here is 1 kHz. The harmonics are always a multiple of the fundamental. So we have the second harmonic, which is at 2 kHz, the third harmonic, which is at 3 kHz, the fourth at 4 kHz, and so on up to the ninth harmonic here, which is at 9 kHz. What about noise? Noise is everything else. All the little nasties in the measurement floor, which is the lowest part of the FFT, which is sitting in between minus 130 dB and minus 140 dB in this screenshot. Due to my heavy use of averaging, you can see the 50 Hz main spike clearly at minus 120 dB. There are also some harmonics produced from the rectifier noise in this area. It may be because I've not yet snubbed the AC voltage at the rectifiers. What about the measurement bandwidth and weighting? So bandwidth is the width of the measurement. For example, in this measurement, the bandwidth is from 20 Hz to 20 kHz, which allows you to see the harmonics all the way up to the ninth harmonic of the 1 kHz fundamental. Later on, when we measure a 20 kHz fundamental, we will need to increase the bandwidth to over 180 kHz to see out to the ninth harmonic, which is at 180 kHz. In order to do this, we need a measurement device with a sampling rate of more than double that bandwidth. In this screenshot, the sampling rate is set to 384 kHz, and that's what I use for these measurements in general. Although the device I use is capable of a 768 kHz sampling rate. In the REW screen, bandwidth, weighting and distortion are all displayed in a box at the top left of the screen, which is circled in red. Weighting is related to a measurement correction curve which compensates for what humans can hear, and it's outside the scope of this video today. Let's have a look at some examples of amplifier distortion performance available today. The Halcro Eclipse Mono at $91,000 Australian per pair. THD is at minus 134 dB at 1 kHz. Wow. The benchmark AHB2 at $3,000 US. THD is at minus 118 dB or 0.0013%. That's THD plus N, by the way. The topping LA90 THD plus N at 1 kHz, 0.409%. Wow. The Macintosh MC152 or Macintosh MC152 at $5,000 US, 0.005% THD at any power from 250 milliwatts to rated power from 20 Hz to 20 kHz. Not bad. The Cambridge Edge W at $7,500 Australian dollars, less than 0.002% THD. The Griffin Apex Stereo, $100,000 US, sitting somewhere around 0.004%. So the Dan D'Agostino Relentless Monoblock, $250,000 US per pair, $250,000 US. So total harmonic distortion is less than 0.007% at 1 kHz at 1,500 watts into 8 ohm. The first watt F8 at $4,000 US, 0.015%. The Audio Research Reference 750 SE vacuum tube mono power amplifier, $65,000 Australian dollars each. Total harmonic distortion, typically 0.5% at 750 watts or below 0.04% at 1 watt. The Hypex NC400, 0.0005% THD plus N at $1,000 US a pair or so. The Cambridge 851W at $3,500 Australian dollars, less than 0.001% or less than 0.005% from 20 Hz to 20 kHz. The Rotel RB1590, $4,200 Australian, 0.03%. The Prima Luna Evo 400, $8,200, 0.1% THD at 1 watt, 2% or less at full power. The Pass XA25, at 10 watts into 8 ohms, it will do 0.0027% THD plus N. The Yamaha RX A6A amplifier, which is a multi-channel amp here, so 9 channels, 0.06% THD, 3,900 Australian dollars. So whilst I could really continue this list forever, because I love looking at amplifiers with nice chassis designs, where does this leave us? I mean, you can pay $800 US for exceptionally low THD plus N performance, or you can pay $250,000 US or more. I guess the choice is up to you. It's very clear that price is not an indicator of low distortion or high performance. Also, there are many factors and performance metrics to consider other than distortion, but distortion is the topic that we're looking at today. So, other measurements and performance criteria could be covered in another video perhaps. Here are the tabulated results for comparison. This list of amplifiers I've chosen for comparison purposes only, so if you see any mistakes, let me know in the comments. All of these amplifiers are from established brands and have niches in the consumer audio market. You can see the extremely high performance Halcro Eclipse sitting on the top of the list at 0.402% THD. Let's move on and take some measurements of the Wolverine amplifier, and we can come back and have a look where it sits in relation to other amplifiers on this list afterwards. So what do I use to measure distortion? the RME ADI2 Pro FSR Black Edition. It has a long name, but it's a very well designed product made by RME in Germany. I decided to get this audio interface due to its very low THD plus N, high flexibility, high connectivity, and the measurement front-end capability that it has. It also happens to be about a factor of 10 less expensive than an Audio Precision AP X555B. And you can apply some measurement techniques to squeeze the best performance out of it. As you can see above, it has very high performance. It also has a very low distortion output. The digital volume control has extremely good performance also. The RME ADI2 Pro FSR manual has some tips on optimal measurement results, because this device was manufactured with this in mind. I've carried out all of these tips and settings. Based on RME's manual, I followed their tips for best measurement results. I made a custom lead which parallels both balanced inputs. I set the interface to output mono to the left channel to improve signal-to-noise ratio by 2.5 dB. I also use mid-side processing and set the input level to less than -10 dB fs. This allows the ADC to have a THD of below -130 dB. A signal-to-noise ratio of 123 dB is achievable. I took note of the recommended bandwidth and the maximum DA levels. The RME literature also discusses the noise level for high-speed sample rates and how it can affect the noise floor. I combined this with a linear audio auto-ranging attenuator Mark II. This device allows me to keep the interface safe when measuring higher power amplifiers. It was designed by Jan Didden of Linear Audio with some input from Matthias Carstens of RME. Its internal silent switcher power supply is run from an external lithium battery pack to reduce noise. I also use a Distortion Magnifier device that I built, which was designed by Bob Cordell. This device allows you to magnify the THD measured by 100 times. I built an external low noise power supply in a shielded die-cast box to power the Distortion Magnifier. Note the use of ultra-low noise LT3045 and LT3094 regulators. This provides power to the Distortion Magnifier via a shielded microphone cable. At this point, I'd like to mention how important the wiring layout and connections are. To be able to measure very low distortion, you need to have a very low noise floor in your measurement system. In order to have a very low noise floor, you need to take care of a few things. Here are some examples. Good connectors and shielded cabling. Use balanced connections wherever possible. Small loop areas. So, for example, input and output leads twisted together tightly all the way up to the connection. This also goes for the test equipment and the load resistor bank. You need to ensure that loop area is kept to a minimum, especially at the amplifier input, output, and power supply areas. Be mindful of your measurement environment and what other devices are powered on nearby. For example, switch off nearby appliances which are electrically noisy, such as chargers, desktop computers, switching power supplies, and so on. These results were only achievable by using high-quality leads and connectors. I prefer to use balanced interconnects where possible. However, a lot of amplifiers have single-ended inputs. In general, the leads I'm using here are comprised of amphenol, nitric, and canard components. Here is the test load I used, comprising of non-inductive power resistors. In this picture, it's configured as an 8 ohm load. When measuring low distortion devices, ensure the connections are solid and resistors with a low voltage coefficient are used. To give you an idea of how sensitive this measurement is, have a look when I turn off and on a nearby 6.5 digit multimeter. Just to give you an idea of how sensitive this measurement is, there's minus 120 to minus 130 dB. See the little spikes there? Here's the DMM. I'll turn it off. Check out those spikes, and I'm just going to reset the averaging. You watch. So you can see, I'll turn the multimeter back on. See that? You can see the basic layout of the measurement system below. Let's take a measurement at 1 kHz. Here's the screenshot of the raw 1 kHz THD measurement of the Wolverine amplifier without magnification over a 22 kHz bandwidth using the RME and the Auto Ranger Mark II. As you can see, it's very close to the edge of what the RME interface can legitimately measure, which is around 0.4056% THD. Except for one mains harmonic spike at around 150 Hz, the noise and distortion are about minus 124 dB down, with a 22 kHz bandwidth A-weighted. Since we're really chasing some low numbers here, we're going to break out the distortion magnifier. The two diagrams above give you a broad idea of the operation of this device. I won't go into too much detail since I could do a whole video on this device alone. Basically, it lets you magnify the THD by 100 times. In the following slides, I will show you the measured THD and the THD plus N using my distortion magnifier at 100 times magnification. I will show you 1 kHz fundamental with THD plus N measured out to the 9th harmonic, and a 20 kHz fundamental with THD plus N measured out to the 9th harmonic. You can see the basic layout of the measurement system, including the distortion magnifier below. Let's take a measurement using the distortion magnifier. Okay, I'm going to try and get all of this in one continuous shot. So, here's the power supply. It's running. The rails are sitting at 59.5 volts or so. Amplifier's running into a non-inductive test load. 25 volts RMS. You can see the attenuator is set at minus 6 dB. The RME is at minus 12 dB FS. Here's the distortion being measured with 100 times magnification. So you've got to add 2 more zeros. There's the number there, 0.0039 THD plus N. So that's 0.4039 if you add the 2 zeros. I would say that's not bad. Check out that number. 0.0039%. Add in 2 zeros and it's 0.4039%. Wow. Here is a screenshot of the 1 kHz measurement. This is not the lowest I've seen with this amplifier. Pretty amazing numbers, wouldn't you say? Let's have a look at 20 kHz now. Here is what the live measurement looks like at 20 kHz with 100 times magnification. The sample rate is 384 kHz and the bandwidth is 182 kilohertz. Okay, same process again. Power supply's running 59 plus or minus 59 volt rails. Amplifier's on. We've got 25 volts RMS on here. Just so you know, that's at 20 kilohertz. Alright, so there's the input lead to the magnifier, which is running. You can see the low noise power supply running there. We've got about a volt going into the attenuator. There's the interface running at about -8 to -10 dBFS. Here's the FFT. I'll let it settle down. I'll just reset the averaging. And here's the number. So you've got to add 2 zeros in front of that, remember? So it's 0.00018, 17, 16, dancing around. But bear in mind, that's magnified 100 times. And look at the frequency span I've got there. So have a look here. How deep we're going. There's minus 120 dB. Okay. There you have it. Out to the 9th harmonic. 20 kilohertz fundamental. I would say 0.00015% THD and 0.00019% THD plus N. As long as I don't, upset it. That's pretty good going. Here's a screenshot of the 20 kHz measurement. 0.00015% THD and 0.00032% THD plus N at 20 kHz. The sampling rate here is 384 kHz. The measurement bandwidth is 182 kHz to capture out to the 9th harmonic of 20 kHz. These are some pretty good numbers at 20 kHz. Let's have another look at the table for comparison purposes. You can see the extremely high performance Howcrow Eclipse sitting on the top of the list at 0.402% THD, and the Wolverine is sitting right next to it. The performance that this amplifier achieves in this regard is truly high-end, and it's a credit to the Wolverine Amplifier design team. The best part about it, you can build one yourself. So that was my baseline THD plus N measurement of the Wolverine amplifier with the current bill of materials and build guide. Over the next few weeks, there are some tweaks the Wolverine team would like me to investigate, but that's a topic for another video. Thanks for watching this far. I really appreciate the feedback and it keeps me motivated to make more videos. For my next video, I plan to discuss further steps in the Wolverine amplifier build and some upcoming improvements. Don't forget to check out the link for the second group buy for the Wolverine PCBs. I'll leave a link in the description. Please register your interest if you've missed out on the first round, or if you simply want more Wolverine printed circuit boards. Thanks for watching. Please like and subscribe if you enjoyed the video. Bye for now.